1.
So I just ran this file, convergeMe, which it's a helper function, but it runs on its own as well. If these variables have been declared by running the main function like this one already, then you can go ahead and run this and see what happens. So let's see which figure first. It pops up a bunch of figures, and these are curves that should be kind of 3D. So there's the adsorption time step, there's the desorption time step, and on the third axis, which we're not seeing right now, is the initial and final. Here we go. The adsorbed mass ratio. So we're seeing that the initial and final adsorbed mass ratio are a result of selecting the desorb step time and the adsorb step time. So you pick a pair of dwell times and you'll get an initial and a final mass ratio once the cycle has converged to a steady state. And this file does not worry about integrating to get to a steady state. It just integrates each step of the process, and then you specify the Q low and the Q high that you're interested in, and it will tell you how long it took to get to those two. So you can kind of see here the plot of the lines is indicating that this was one point in that array where we said Q low is 0.06, something like that. And then this line means we said that Q high was just less than 0.1. So then it looped through the 2D array and it figured out what would be Q low corresponding to that value of Q high. And then you build an array that's a two-dimensional array of the Q low and the Q high and the resulting time steps. From the time steps, you can calculate the total cycle time, and from the mass ratio, you calculate the cooling capacity. And then this line right here is indicating that that particular pair of time steps and that Q low, Q high value, that's what it thinks is an optimum for cooling capacity from this system. And then here's what it would look like in the time series. The bed that is desorbing, the mass ratio is dropping like this over time. The bed that's adsorbing, it's increasing like this, and you just cut it off at whatever high and low values on the y-axis, and then you would interpolate from the start time to the end time, and that gives you the actual dwell time. So this is not a physically significant time, it's just the time it takes to go between two given values of the adsorbed mass ratio. Here's some kind of a contour plot, I guess, with cooling capacity. And then it's a little bit unhappy, depending on how you tell it to plot things. It doesn't always like them. And I think this align axis labels is a file I downloaded somewhere from MATLAB Exchange, possibly. Maybe I have to tell it to add this folder to path. So if you download that, add it to the path, then it should stop giving this kind of error message. So this is basically the summary. We had a revision of the original main loop, and then there's some helper functions. This kind of demonstrates what are the steps in one cycle of time integration scheme. This is a novel helper function. that does this interpolation, selects the optimal dwell times for max cooling capacity, something like that. And so you can see that this is where it's doing the maximum. I'm masking off places where there's a negative time step. In other words, it should always be going from low to high, high to low during the appropriate steps. So we do the maximization of this. This is just an array. It's giving index for the first column and then the index for the second column, or for, I guess, the first dimension and the second dimension, and then telling me that index first dimension and second dimension, and then we can go in these variables I've created during the loop and assign the optimal times for each step explicitly, the cooling capacity and the coefficient of performance, and plot things. So that's what's happening in this file, and then a lot of unnecessary plotting as well. So there's another file that encapsulates one use of the Freundlich equation. So going from the adsorbent bed pressure, or temperature I should say, and the saturation temperature, in other words, given the pressure of the refrigerant, assuming that it's at equilibrium, it tells you what is the current adsorbed mass ratio, so this encapsulates that functionality. There's another file in here which is just kind of a sketch, a worksheet for calculating, comparing the pressure functions. So this was in the old code something like this, or this line, and then this calculates the saturation pressure curves given each of those functions. This one I'm calling good. It comes out of CoolProp. This one is, like I said, a polynomial fit. The dissertation actually has, I think, what's called an Antoine equation of this form, an exponential term, and its derivative looks like this. And so somewhere in my notes I've compared these. So that kind of wraps up the MATLAB code that's there. I'm going to also show what is the history on that. I can pull up GitHub. So it takes a little bit of time, one moment. Okay, so opening this takes a long time on my computer, but just to show you, all this was about first 2 weeks in April 2016, going from the initial commit, just modifying some files, and I'm adding this function, helper functions, and then a lot of changes here, adding these new optimization studies, and I'm just cleaning things up. One thing to note is I do not usually commit images, so these are the outputs, things I saved when I run the files, because the images could be quite large, binary files. Vector graphics are pretty nice, and I try to use those. They're smaller files, and that's about all from the MATLAB code. So next I'll try to talk about the EES model.